So let's continue finishing up what we where we left off in the lecture of this separation of variable problem. So we were trying to solve this for the Laplace equation, and with certain boundary conditions, where just a quick recap, where we want from 0 to a on x, and for y, and we want t to go to 0 over here, here, here. And on here, we want t to equals to a certain constant, okay? So this is the part inside where we want to solve, this is the domain where we want to solve it. And we use a separation of variable up to this point where we found that we have two equations like this, 0, and with the appropriate boundary conditions of basically I want x at 0, whatever y is, I want, as long as x equals to 0. You can see that, right, we were, this is the key part about separation of variable. We're letting this multivariable function equals to a product of single variable functions like this, x of x, y of y like this. And so as long as little x equals to 0, right, I want t equals 0. So I basically want this to be 0, x of a to be 0 for the same reason, right? So I want t to be 0 here. That means this part, no matter what y is, the only way, no matter what y is, to make t 0 is better, this piece, as long as little x equals to a, capital X equals to 0, right? So similar thing over here. Whatever x is, right? Whatever x is, as long as y equals to 0, I want it to be t naught. And as long as y equals to infinity, so basically y tends to 0, as long as y tends to infinity, independent on what x is, right? So these are the, after I separated into the component functions, these are the relative boundary conditions of the original problem. Okay, so this is where we were, and because we need this to be oscillatory, right? So this to be, we want it to be sine and cosine for x so that it can match up. That's the only way where you can create a 0 on both sides, probably like a sine, you can imagine, right? So we'll see the only way to make that happen is when lambda is negative, right? So you will get some oscillating behavior for it. So the way to do that, to ensure that we can let lambda equals to k square. So just make another variable instead of lambda. Remember, lambda is just something we invented anyway to ensure the separation of variable equals to a constant on both sides. We didn't. We want to find out what lambda is, but we're not tied to lambda. We can use a different variable. And this, if we write it this way, this ensures this is less than 0, as long as k is any real number. Right? As long as it's not imaginary, we can ensure that we get a x double prime plus x, right? Plus something x. So we have a simple harmonic equation, which gives us a solution like this: a cosine kx plus b sine kx. Right, now we can adapt the boundary conditions over here. So the zeros are always easier. Okay, so we're gonna we're gonna apply the boundary conditions of 0 equals to x0. So x0 meaning a cos 0 plus b sine 0, right? So this just goes away, and this equals to 1, right? So what do we have? We basically have a equals to 0. Okay, now we also want, so this is one conclusion, we'll just remember that. And now we also want xa to be 0. So we know that a is 0, we will just write b, the b part. So we have ka like this. Now we can have two choices. We can have b equals 0 or sine ka equals 0. So b equals 0 is not so good, because if a and b both are 0, we just get some trivial solutions. We just get 0 for t, which is not so good, right? And it doesn't really satisfy this anyway. So we are going to instead want b is not 0 and sine ka is going to be 0. And this happens when you look at the unit circle. This happens when ka equals to any integer of pi, like that. A is a constant we know, K is a constant we don't know, right? Anything else we do know. So we basically find, right, a series of solutions. We don't have a unique solution for K, notice, right? We have infinite solutions of K as long as n is an integer. We have K, so we'll just write Kn. Now, because it's a linear PDE, then adding all the solutions together is also a solution. A linear combination of the solutions is a solution, right? So we have, so each of these little xn, right, they can have different coefficients, right? Sine Kn, each of these are solutions. So just to write it more explicitly, right, we have sine n pi over a, oops, sorry, this should be x. If you look over here, right? So a is 0, so we don't need that. Here we know what k is. K should be this, right? So you plug that in, so it's that. Okay. And the full x, right? The full x should be, you add up every possible x's, xn's. So that is a solution. Okay, now we have basically the x part of it. Now we want to find the y part of it as well. And so the y part, we go to y, because now that is a almost a simple harmonic equation, but with a positive, right? So this is going to be simple harmonic. If this one is sine cosines, the other is going to be exponentials. Right. So we are going to write e minus ky plus deky like this. So that's the solution to this one. Okay. Now we are going to implement the boundary solutions. With exponentials, the tip is it's always easier to start with the y goes to infinity, right? So we'll write that. So y better goes to 0 as little y goes to infinity, right? So when little y goes to infinity, what happens? We'll abuse the notation a little bit, right? 0 equals, you know, y goes to infinity. I was going to just put infinity in there, but let's make it a little bit more rigorous. So it's a limit, y goes to infinity. So this part just goes to 0 plus d, and then this part is right? This is rough, this is bad rigorously, but we're going to work with this. This is going to be exponential, right? The only thing we can ensure the left-hand side and the right-hand side matches is if d equals to 0. Okay, so this is a classic argument, appears over and over again. So basically we need d equals to 0, right? So the first boundary condition, if we would look back over here, the first one tells us a equals to 0, and the second boundary condition tells us k has to be this. The third boundary condition, which is this, tells us d equals to 0. And the last one is where we need to implement, right? So far, I think where we left off in class is we have, well, t of xy is, well, x times y, right? This is how we broke it up, just to recap. And now we realize it's bn. Well, so d equals to 0. So d equals to 0 over here. So we only have this part for the y, and the x, we have this part, right? So we kind of copied that part, but then there's a c as well. So these two constants are going to be multiplied together. And when they multiply together, it's just a new constant. Okay, so we're just going to say, hey, there's a new constant. You can just keep it as b or whatever, as long as you understand that's a different constant or a constant. As long as it's a constant, it's fine. N pi x over a e to the minus the k. I know what k has to be in order to satisfy the whole thing. So we're going to put that in as well, n pi over a y. Okay, now just a little tidying up is technically n can be anything. At this point, when we were at this point of the solution, n could be any integers, including negative numbers. But if I have negative n over here, I just spoiled the whole argument that I want this exponential term to go away, right? So what I need is, I cannot accept anything that is n equals to negative. another way to think about it is for n equals to, if n is negative, I need to take the c equals to 0 solution, right? So you need to break it into two bits. You need to break into one part where n is positive, and then one part, add another part that n is negative, but then they'll recombine anyway, right? So the shortcut is I just reject anything where n is negative. I could start from 0, but you see that's a little bit redundant, because if n equals to 0, then it's just the whole thing is 0. So it's not going to really contribute. So just to save a little bit of tidiness, we're going to start with n equals to 1. Okay, there's one more boundary condition. So we haven't, so we applied one boundary condition here, we applied the second one here, we applied the third one over here. So the last one is where we always take care of the ones that goes to 0 first, and then take care of this last, okay? So now we have, we want, so let's write this out one more time, what we have. So we have this, n pi x over a, e to the minus n pi over a y, right? This is n pi over a x, n pi over a y. Okay, so now we want at y equals to 0, this whole thing equals to t naught, right? Whatever x is within the domain, of course, within the domain of 0 to a. As long as y is 0, we want that to equal to this, right? So let's plug this in and see what happens. So we have n summing from this to infinity, sine n pi x over a, right? And we have y equals to 0, so that's just 1, okay? All right, good. What is our goal? Well, our goal is to find, with boundary conditions, we should be able to find out all the coefficients, all the unknown coefficients. So our goal is to find En, all right? So here's the trick, right? So the trick is called projection. So project, we're gonna project out En. And how do we do that? We're gonna multiply both sides by sine mx, m pi x over a, because we know this is the orthogonal function to sine n pi x over a. Okay, so I'm going to multiply both sides, take this, multiply both sides by the orthogonal piece of this. Okay, so here's the part where you want to kind of memorize or know where to find, at least really quickly, is these two or three identities. So this one is good to know, and it's L times delta NM. It's the same thing with cosine, x over L, sine n pi x over L dx. It's also L times NM, delta NM. And if you have sine and cosine together, it's going to be 0 because this is an odd function. Right? You check the integrand, it's odd. And I'm integrating from symmetric domains. That is left and right, it's the same amount. But if it's an odd function, then the left-hand side bit is going to cancel the right-hand side bit. Right? So this is odd in terms of x. Both of these, that's cosine, sorry. So both of these are even, both of these are odd in terms of x, so the whole thing is going to be even, okay? So we have a sign over here, so if I multiply this and then take this integral, then I can get rid of, I can project out, it's like shining out, I want to get the En, or this coefficient Em on its own. I want to make it a subject, essentially, and this is the trick. Using the orthogonality relationship between the sines and cosines, I can project out, I can sort of pull out the En. Okay, so the next thing is I'm going to integrate both sides, dx, right? So integrate dx like this. Where should I integrate it from? Well, this side only makes sense when x goes from 0 to a, right? So that's all we can do from 0 to a, because if I make this any larger, I have no idea what the left-hand side of this is. The only thing I know that, well, this only holds, right? If you think about it, there was a condition where x only holds from 0 to a, right? So I can only integrate because if I integrate anything more, I don't know what is it still T naught? If I go back to here, right? If I go outside in this domain, is it still T equals to T naught? I don't know. So it's better if I just do this part of the integration. Okay, so that's what we're going to do, 0 to A. Okay, we're going to do either side separately. Let's do the right-hand side first to get the projection of that. Right, so we'll separate it out, do it bit by bit. The right-hand side, over here, I'm integrating with respect to x, so anything that has nothing to do with x can be pulled out. Sine m pi x over a, sine, oops, sorry, that's a, n pi x over a dx. Okay. Now I want to make use of one of these identity, probably this one, right? But I need a symmetric domain. Here I have 0 to a. So let me extend that to minus a over to a. Now I can do that if and only if, right? This is a even function, which means if it's the same on both sides, right? If I want to integrate from 0 to a, then if I integrate from minus a to a, that's the same as me integrating just this part, but doubled. So I need to half it, right? So if I multiply by 1/2 in front, so if I integrate from minus a to a, I basically have over integrated. I found 2 of the area, so I divide by 2. It should be the same as this. So this is an equal sign. So just understand this line from 0 to a, right? From 0 to a, just to emphasize that, right, is half of integrating from minus a to a, like that. Okay, as long as this is an even function, even integrand. Okay, all right, good. Now I can just quote the result. This part, right, it's equals to a times delta nm. If you look back at the identity on top over there. Okay, now I'm summing over here. So the quick answer is this is just em times half a, like that. But where does this come from? Is because you can split this into all the n's that are not equal to m plus the term, right, where n is equals to m. So it's n is equals to m. So this delta and m is equals to m, like this, right? So this actually equals to, right, this chunk. Well, n has also go from 1 to infinity. Right? But all the, and then this one specific term, I'm just gonna pull out that term over here. So if n is not equals to m, this is gonna be 0. So all this term, the first term is gonna be 0. And then here, this is gonna be 1. Right? So I basically just have this. Okay, so the quick answer is, quick way, whenever you see a summation, delta nm, it just projects out, it just extracts out the em bit of this, 1/2 a. All right, so that's the right-hand side of this huge orange and blue and black mess. Now let's do the left-hand side. Okay, so the left-hand side is pretty simple in respect of this. Okay, so now this is just a simple integration. There's nothing more to say other than write this through. So you can just follow through here. So I'm just gonna integrate this. So sine becomes a cosine. I usually write this part first and then worry about the sign, whether I need an extra positive or negative. And if I integrate a sine, I think I need a negative up here. All right. And now we just plug things in here. So we have cosine m pi minus 0. So that's 1. Okay. And we know cosine m pi is equals to minus 1 of m, as long as m is any integers, which is what we are going to impress on, right? So I'll just take this minus sign and flip this around just for niceties. T naught. So I have 1 minus this. So now I just need to combine the left-hand side and the right-hand side together, and I find my EM, right? So I have EM equals, well, times this. So therefore, let's write that. It's A M pi T naught 1 minus this. And EM, so I'll just multiply this side, divide that over, and I have 2 T naught over, and I'm going to just change the M to N just for tidiness, because M or N is just an integer and a dummy variable. So I can just change that to an N because I want to just use my previous formula of summing over N over here. Okay, all right, so that's one way to write the EN if you like. So this is perfectly acceptable. And I just need to put things together as the T of XY and I'm done, right? This is perfectly acceptable. Another way is you can write it as T N pi multiplied by, it's 2, right, if N is odd, and 0 if N is even, right? So it's also the same as 4 T naught over N pi if N is odd, and 0 if N is even. Okay, and we're almost done. We just need to piece everything back together. All right, so therefore T of XY is sum N from 1 to infinity. What's this big En? Well, it's 4. Well, it's 2 T naught over N pi. Remember, 2 T naught over N pi, and then multiply this piece of 1 minus 1 to the power of N times sine of N pi x, N pi over A times X, and then e to the minus, because now we are putting the full solution over here, N pi over A y. Okay, and that's the full solution. All right, so another way to write this is it only has support, otherwise it's 0, right, if N is even. So it only has support when N is odd. So I can replace all the N's with, and this will equals to 2 if N is odd, right? So I can replace this. So there's 2 ways I can write this. I can write it like this, N odd, right? So this will equals to 2, right? So it's 2 times 2, it gives you 4. And sine, this is perfectly fine, by the way. This is a perfectly fine solution presentation as well. But if you find it clunky, this is another way to write it. I kind of like this, but some people are unhappy with sort of having an extra condition. I would just write, comma, N odd. That's perfectly fine. You should get full marks if you write this in an exam because it's correct, right? N is odd. Some people don't like having too much fine prints, subscripts over here, in which case you can use the trick where you change, you want odd numbers, right? So you just write 2n plus 1. So now you're guaranteed to have odd numbers over here. So it's much cleaner. So each of these 3 presentations are all fine. So all of them are fine, and each of them has kind of its pros and cons separately. Okay. Yeah, so you see, yeah, each of them has its pros and cons. The first one, the pro is this is nice. This part's nice. This part is a little bit clunky. The second one, everything is pretty nice, right? You can even pull out this part out in front. Oh, not the N. The N needs to stay inside, but this part can go outside. Anything that has nothing to do with N. So everything here is nice and clean, but this part is a little bit awkward. The third presentation, this part is nice. I got all the odd numbers over here, right? But here it's just a little bit annoying with all these little extra bits. So each of them, all of them has their merits, pros and cons. But this is basically the full solutions. Okay, all of them should be right. All right. So long question, but hopefully you see the separation of variable part is the part where we discussed, and then the tricky and then it's applying boundary conditions. So there's 2 steps. The first step is well, I always like I said in class, you always want to sort of dissect and understand the question first, and have a visual way to visualize it first, and then now do the separation of variable, which gives you ODEs, and then now just apply the boundary conditions one at a time. Usually you should get 4, so 2 for each, or yeah, so whatever the appropriate boundary conditions are, depending on the heat equation, or if you have 2 second ODEs, you should expect 2 boundary conditions for each of them. All right, so let me know if you have any questions, and yeah, so good luck.